Hello, this is part 5, I think, of my little study on electricity that I'm just doing kind of for fun. Although in this episode, this exciting episode, instead of talking about electricity, we should just talk about Christmas lights. That's right, Christmas lights. Have you ever wondered why sometimes you're putting up Christmas lights and certain brands, if one bulb goes out, what happens to the whole string? The whole string goes out, doesn't it? That's really annoying. Unfortunately, fortunately, not all brands are that way, but some brands are that way. We'll talk about that, and it'll be a helpful study in the process of some concepts concerning electricity. So let's review what we talked about real quick in the last little episode. So we talked about electricity, and just to kind of review, I don't want to go back over the whole thing too much, but we talked about the three letters, E-I-R, okay, where the E in an electrical circuit represents the force or the pressure. This is the force that moves the electrons and causes the electricity to flow. It's not the movement itself, it's the force. So that E, that force or pressure, electrical pressure, is measured in what? Volts. That's right, volts. So remember, 1 volt is the amount of force required for 1 coulomb to produce 1 joule of work. Okay. We also have a motion component to any given electrical circuit, and that is represented by the letter I. So the letter I in an electrical formula represents the movement or the current flow in a given electrical circuit. And what is the current measured in? Amps. That's right, amps. And remember that amps is simply 1 coulomb flowing past a given point, or well, let's state this more accurately. 1 amp is simply 1 coulomb moving past a given point, a fixed point, per second. Okay, so that is the measurement, the unit of the amp. And remember also that 1 coulomb is just 6.25 times 10 to the 18th power number of electrons. Okay. Then we talked about a final component last time. We talked about R, and R stands for the resistance to current flow. If you didn't have a certain amount of resistance in a given circuit, what would happen is that negative potential and the positive, the negative would try to get to the positive side as fast as it could, and this would cause a huge amount of current to flow, and the wire would heat up really fast and probably even burn up. That's called a short circuit. So you want a certain amount of resistance to current flow to prevent that. Now, a lot of times resistance in a circuit could be things like a light bulb, where the filament it's not a very good conductor. So for example, they use tungsten in incandescent light bulbs, and that tungsten filament isn't really a very good conductor. So what happens is it builds up a lot of heat, and that's the energy, and that as it gets hotter and hotter, it begins to glow, and then it produces light. So that light, that heat that you're seeing, is resistance to current flow, and that's measured in ohms, if you think back to the previous episode. So we drew this little circle. Let me back up so you can see the whole thing here. We drew a circle where you can kind of just remember the basic electrical formula, where the E is the volts, and it's on the top. And it's on top because it is the bigger quantity. So what happened to my little camera there? There we go. Autofocused or something. So the E in this formula is the voltage, and it's the amount of electrical pressure that's required to push a given quantity of amperage or current through a given quantity of resistance. The basic formula is written this way: the E, or the volts, equals the current flow in amps times the resistance measured in ohms. This formula can be rearranged, remember, by covering up the quantity that you are looking for. So let's say that we know the voltage and the current, but not the resistance. Well, we cover up the R, and we're left with E over I. And that would be our formula right here. The E divided by I equals R, or resistance in ohms. Or let's say that we knew the resistance, but we didn't, and we knew the voltage, but we didn't know the current. Well, if we cover up the I, we're left with E divided by R, and that would be conveyed in this formula right here. E divided by R equals I. So that's our basic formula. I'm going to drink real quick, excuse me. Now, let's see how this works in a real circuit, or at least an imaginary sort of real circuit that I've drawn out here. Let's say that I have a circuit and the source voltage, in other words the electrical pressure that I have, is a difference in potential which amounts to 12 volts of electrical pressure. I hook up my ammeter and I get a reading across the line of 0.5 amps, in other words half an amp, that's flowing through my copper wire. I do not, however, know what the resistance is, what's the resistance to the current flow is that's hooked up right here. Now, do I have to get some kind of a meter, an ohm meter, and measure this out, or can I just figure this out by using my formula? Well, actually I can, because I have two quantities that I know. I know the voltage and I know the amperage, but I don't know the resistance. So let's cover that up and let's apply our, there it is, let's apply our formula, and we have E divided by I, and that should give us the R. So let's see if it works. Okay, so I know that the source voltage coming out of the wall is 120 volts, and I know that it's producing a current through my circuit of 0.5 amps, so I write that in, substitute the E with the 120 volts. I substitute my R with, the I, the amps, with 0.5 amps, and then I just divide that out, and it gives me a resistance of 240 ohms. And notice that I represent ohms with the Greek letter omega. So that means that my resistance to current flow at this point, this load here, could be a light bulb, it could be an actual resistor, it could be any number of things, it could be a heating element or something like that, that it is producing 240 ohms of resistance to the current flow, and given our electrical pressure, our force of 120 volts, that's going to produce an overall current of half an amp, or 0.5. And that's how the basic formula works out. Now, I started out this episode by mentioning that I wanted to talk about light bulbs, and I mentioned the terrible problem that comes up about this time of year where you hook up your Christmas lights and you plug it in and you're all excited, you got the kids out in the front yard, and then nothing happens. And then all of a sudden you have all of your kids crying because you didn't make the magic happen. Well, what happened? If you have a particular brand, a lot of brands are still this way, where you plug it in, and because it's wired in series, there's only one pathway for the current to flow. So if one of the bulbs breaks, it's like a switch flipping open, and so now there's not a pathway for the current to flow, and so the whole string goes out. Now let's talk about this a little bit. So I devised this chart, or this little diagram, or whatever you want to call it, to talk about series circuits, because there are some properties about series circuits that you want to know about. Okay, so boy, it's kind of freaking out here. I hope this works. Let's see, let me get a little closer. Okay, so right here I have drawn this circuit. It's kind of hard to see possibly, but because the camera keeps auto-focusing, but on the far side here, let me step out this way. Okay, oops, there we go. On the far side here, I have the voltage source of 120 volts, okay? And then I have three resistors labeled resistor 1, resistor 2, and resistor 3. Now let's say that this is the shortest string of Christmas lights that you've ever seen, and each one of these R values represents one light bulb. That's the heat that's generated by the filament which is actually a sort of resistance to current flow. And when we measure these out, we find that each light bulb produces 50 ohms of resistance. So let's say, though, that I don't know what my total current flow is. Okay, well, let's look at some rules concerning series circuits. Now, just looking at this diagram, we have one wire that's represented by my line that forms a loop through the three resistances back to the voltage source. How many different pathways are there for current to flow in this circuit? Only one. This is a series circuit, and what that means is that all of the electrical current has to flow through R1, and then it has to make its journey through R2, and finally through R3 to get back to the voltage source. Okay. Now, there are good things about this, but there are also some negatives. And let's talk about the electrical principles involved here. First of all, since there's one path of current flow through the whole circuit, that means that if I were to measure the current at a given point in the circuit, it's going to be the same throughout. So if I measure the current right here, it's going to be the same as it would be at R2, and it would also be the same as it is at R3. Okay? That's because there's only one path for the current to flow. That can be both an advantage of a series circuit, but it can also be a disadvantage. Let's go back to my practical example now. I'm hooking up my big 3-string lights set here for the Christmas lights. It's a really big string of 3 bulbs. But let's say that R3, the filament's burned up. So now there's a big gap here. There's not a place for the electricity to flow from one side of the R to the other. Well, since there's only one path for current to flow, if you think back to our earlier video, what was one of the things that we need for electricity flow? We need a complete path or loop. So because this R3 is burned out, because there's no longer a complete path for the current to flow from the negative terminal back to the positive terminal, guess what? No current flows at all. So not only is the light bulb represented by R3 out, but so is R2 and R1. This is a downside to series circuits. Now, how can we, and I notice here that I do have some values, some numerical values already listed. I know that each light bulb offers 50 ohms of resistance to the current flow. And I know that my source voltage is 120 volts, but I do not know the total current that's flowing through my circuit. Well, how can I find that out? Well, let's review our principles here. So we know that there's only one path for the current flow, and that means that the current is going to be the same at all points in the circuit, at all of the resistors. This also means that the voltage drops across the various resistors, all added together, should equal my source voltage. We'll talk about this in a minute. It also means, unfortunately, that if one resistor fails, it's going to stop the current flow to the entire circuit. Okay? Now, how do I find the total resistance? Because remember, my formula for finding the total current is, let me get my other paper back out. If I want to find the total current, I have to, where is it? There it goes. I have to divide the total voltage by the total resistance. Well, how do I get that if I have multiple resistances? Well, in a series circuit, you simply add the 3 values together to get your total. So since there's only one path for current to flow, that means that all of these individual resistors are, if you're looking at it from the point of view of the source, let's say that you're standing like you'd be standing in an electrical circuit, but let's say that you were. Let's say that you're standing right here at the voltage source, and you're trying to push a certain amount of electrons through this whole circuit from your negative side to your positive side, because you want to become more positive, I guess. Well, what that means is I'm going to have to push all of those electrons through each one of these resistances. So to get the total resistance, we simply add them together. So we have 50 volts for R1, 50 volts for 50 ohms for R1, 50 ohms for R2, and 50 ohms for R3. We simply add those up, and we get 150. And then we apply our formula. 120 volts divided by 150 ohms gives us 0.8 amps. So that's the total current that's flowing through our circuit. I can measure the current flow at each one of these points at R1, R2, and R3, and I should read 0.8 amps as my total current, or as my current value, because the current is the same through all points of the circuit. So just to review, and we can write these out in a formulaic fashion. I total, IT, I sub T means I total equals I1. That is the current at resistor 1 equals I2. The current at resistor 2 equals I3. In other words, it's all the same. The total resistance is equal to the sum of each individual resistor. And the total voltage is equal to the voltage drops at each individual little voltage point. Now, because this video is getting long, I'll finish up talking about voltage drops in another video. I have to break this up a little bit, but I hope that you learned something about series circuits today.